Hi and welcome to this third video of my playlist about the preparation of aryl amines. This video is about transition metal catalyzed aromatic nucleophilic substitutions, mostly of aryl halides with amines. Over the last 30 years, these reactions have been thoroughly investigated. Their main problem is that large quantities of expensive catalysts are sometimes required, what increases the cost and complicates the purification of the final product. Moreover, many reported examples require strong bases and sometimes further additives, what makes the optimization of such reactions difficult. Nevertheless, with some catalysts, even unreactive aryl chlorides can be aminated under relatively mild conditions. Aromatic nucleophilic aminations can be roughly organized into three main strategies: uncatalyzed substitutions, which are discussed in part 2 of this playlist, palladium and nickel catalyzed substitutions, and copper catalyzed reactions. Metals like palladium and nickel usually require bulky, electron-rich phosphines to act as catalysts, while copper-based catalysts work best with amines, carboxylates, or pyridines as ligands. Let's start with copper catalysis. Copper and the required ligands are much less expensive than palladium-based catalysts and should therefore be tested first. The mechanism of most copper-catalyzed aromatic aminations is sketched here. Deprotonation of a copper amine complex yields an electron-rich copper amide, which reacts with the aryl halide in a slow, rate-determining step. Reductive elimination of the aryl amine then regenerates the catalyst. One important difference to uncatalyzed substitutions is the rate dependence on the leaving group. While in uncatalyzed substitutions fluoride is the best leaving group and iodide the worst, in transition metal catalyzed substitutions this order is reversed. Aryl iodides react fastest, while aryl fluorides do often not react at all. Here, for instance, only chloride was displaced when chlorofluorobenzene was treated with benzylamine and 5% of a copper oxalamide complex. The reaction still required 120 degrees Celsius and DMSO as solvent, but no substitution of fluoride occurred. In this example, 2-chloroanisole underwent nucleophilic amination with hexylamine. Despite the high reaction temperature, no aryne was formed, because the base was too weak. The main product was that of ipso substitution of chloride. Aryne formation in this case would have yielded a 3-methoxyaniline, as discussed in the previous video of this playlist. Here a special solvent was used, namely a mixture of glycerol and choline chloride. This enabled the clean phenylation of a primary aliphatic amine with bromobenzene. The reaction already proceeded at 60 degrees Celsius and was complete after 12 hours. In this example, a proline derivative was arylated at nitrogen with a 3-bromopyridine. 10% of copper iodide was the catalyst, and no additional ligand was required. Phosphate is only slightly more basic than carbonate, and no racemization occurred. Here again an aryl bromide was the electrophile and 25% of a copper diamine complex the catalyst. No arylation of the diamine occurred, probably because the aminopyrimidine was deprotonated and therefore more reactive than the neutral aliphatic amine. Let's now have a look at palladium and nickel catalysis. These reactions usually require much stronger bases than copper-catalyzed substitutions. The rate-determining step is insertion of palladium 0 into the carbon-halogen bond. Reductive elimination of the aniline then regenerates the catalyst. Bulky phosphine ligands are required to generate reactive, coordinatively unsaturated palladium 0 complexes and prevent the precipitation of metallic palladium. Unlike copper-catalyzed or uncatalyzed aminations, here the preferred solvents are non-polar, aprotic solvents like toluene or ethers. This is an example of a nickel-catalyzed nucleophilic amination of an unreactive aryl chloride. The ligand was BINAP and the substitution already proceeded at 50 degrees Celsius. An excess of sodium terzbutoxide was required as base. If this reaction had been attempted without the nickel catalyst and by intermediate arine formation, a different isomer or a mixture of isomers would have resulted. Here, only 0.5% of a nickel phenanthroline complex was sufficient to bring about a clean arylation of pyrrolidine with an aryl chloride. Sodium terzbutoxide, DME, and a reducing agent were also required. The role of the reducing agent was probably to stabilize catalytically active nickel-0 complexes. Similar effects have been observed in palladium-catalyzed substitutions, where metallic zinc is sometimes added to increase the reactivity of the catalyst. Here, the ligand probably also reacted with pyrrolidine, and one may wonder what the catalyst really was. Fluorosulfonates can be prepared from phenols and sulfuryl fluoride. Because bimolecular substitutions at hexavalent sulfur are slow, fluorosulfonates are suitable starting materials for aromatic nucleophilic substitution. Here, aniline was arylated at nitrogen by such a fluorosulfonate with the aid of a nickel catalyst and lithium terzbutoxide as base. In this example, a highly reactive palladium-carbene complex catalyzed the arylation of cyclohexylamine with an aryl chloride. Only 0.25% of catalyst was required and the substitution already proceeded at room temperature. Here, a palladium-catalyzed aromatic substitution succeeded without a strong base. With BINAP as ligand and cesium carbonate as base, the arylation of methylpiperazine with an aryl bromide was achieved by heating to 125 degrees Celsius for 3 hours. No substitution of fluoride or saponification of the ester occurred. Also, nitride can be a suitable leaving group for palladium-catalyzed aromatic substitutions. With potassium phosphate as base, hexylamine could be cleanly arylated with 4-nitroanisole in this example. A high reaction temperature and a bulky phosphine ligand were also required. Here the leaving group was methane thiolate. Despite the ability of this leaving group to form strong bonds to transition metals, 2.5% of a palladium-carbene complex and an excess of a strong base were sufficient to bring about a complete arylation of toluidine. In this example, a rather sophisticated palladium catalyst was used to arylate 3-aminopyridine with an aryl bromide. With DBU as base, the substitution already proceeded at room temperature and was complete in only 3 hours. When a direct arylation of ammonia cannot be achieved, one convenient synthetic equivalent of ammonia can be benzophenone imine. This remarkably stable imine can be prepared by addition of a phenyl-Grignard reagent to benzonitrile. In this example, benzophenone imine was arylated at nitrogen with an aryl chloride, an excess of sodium terzbutoxide, and 1% of a bulky palladium complex. Hydrolysis of the arylated imine yielded the corresponding aniline. This specific example may also have worked without any catalyst at all, just by intermediate arine formation. Also, amides can be used as synthetic equivalents of ammonia. Here, a picoline amide substituted bromide of a bromofluorotoluene without any fluoride displacement. The base was a mixture of DBU and sodium trifluoroacetate, and only 0.5% of palladium was enough to attain an acceptable reaction rate. Phenols must usually be converted into sulfonates to become suitable electrophiles for nucleophilic substitutions. But with the rhodium catalyst shown here, it was possible to aminate phenols directly. Let's check some potential side reactions. Obviously, primary amines may be arylated once or twice, as in this example. Despite the excess of primary amine, substantial amounts of diarylamine were formed in this instance. Anilines are more acidic than aliphatic amines and may even be deprotonated by carbonate. The metallated product can react faster with the electrophile than the starting neutral amine, and thus cause the formation of large amounts of diarylamines. Here, by varying the solvent and the amount of base, the yield of byproduct could be lowered to around 5%. Other typical side reactions include the formation of biaryls and the reduction of the starting electrophilic arene. Because amines with alpha hydrogen are good hydride donors, reduction can occasionally become a serious issue. Even unreactive arenes can react with aryl palladium intermediates and yield biaryls, as shown here. Small quantities of biaryl byproduct can be a complete no-go for a palladium-based strategy, because the acceptable levels of, for instance, chlorinated biphenyls, both in the products and waste streams, are extremely low. This is an example of palladium-catalyzed aromatic amination with extensive reduction of the starting aryl bromide. It may take significant optimization efforts to overcome such a problem for a given pair of starting materials. In this example, a fourfold aromatic substitution was attempted, but again, large amounts of reduced arene resulted. Alkoxides can compete with amines during aromatic nucleophilic substitutions. Terz butoxide usually adds too slowly to arenes, but primary or secondary alkoxides react much faster and may also act as hydride donors. In this example, a chlorobenzene underwent clean palladium-catalyzed substitution with sodium ethoxide at room temperature. At 50 degrees Celsius, however, a large amount of reduced arene resulted. Thus, one strategy to prevent reduction may be lowering the reaction temperature. Because of the high complexity of transition metal catalyzed substitutions, the effect of solvents and additives can be difficult to predict correctly. Although most of these reactions proceed well in toluene or dioxane, in this case a high yield was only obtained in wet terzbutanol as a solvent. This again shows that the large number of parameters makes these reactions truly difficult to optimize. Not all solvents are compatible with the strong bases required for transition metal catalyzed aromatic aminations. Polar aprotic solvents may react with these bases and cause the formation of byproducts. For example, cleavage of DMA or DMF can lead to dimethylanilines as byproduct. Non-polar solvents can be more resistant to strong bases, but heterogeneous reactions are still more difficult to optimize. Thus, the choice of solvent is a critical parameter and should not be underestimated. Further side reactions caused by tertiary alkoxides include cleavage of various carboxylic and carbonic acid derivatives, beta eliminations, the isomerization of alkenes, and hydride migrations leading to the reduction or oxidation of functional groups. Here are some further examples which you can also find in the description of this video. The next video of this playlist is about the preparation of arylamines by oxidative degradation of benzoic acid derivatives and aryl ketones. Benzoic acids are readily accessible from alkyl benzenes, and their transformation into anilines can be of interest in special situations. See you then.